I'm assuming that you just watched the Illuminati confirmed video and that you're a hardcore mathematician and that you now want the proof that your Morley's theorem really works. So I'm going to give you the proof now. And it's going to be an absolutely amazing proof. Now, this Morley's theorem is notoriously hard to show. It's very messy. It used to be very messy until recently when my favorite mathematician in the whole wide world, John Conway from Princeton University, came up with a very, very beautiful, accessible proof. And so I'm going to try and make it even more accessible by animating it the way I do it here on Mathologer, okay? So it's my tribute to John Conway, but also it's just an absolutely beautiful thing. So one should have a proof somewhere. Well, just in case you haven't watched the Illuminati confirmed video, maybe you just go there and watch it. But just a quick recap, what happens is you take an arbitrary triangle, you trisect the angles, and we kind of cut them into 3 equal pieces. And then you extend these cuts, and they meet in 3 points. And the 3 points always form an equilateral triangle, which is something absolutely miraculous. It's called Morley's miracle. And here's a proof. Here's that amazing proof. Okay, so the only thing we really need here is that the sum of the angles in a triangle is 180 degrees. Everybody knows this. Next thing we need to, kind of just remind ourselves that 6 times 60 is 360, right? So if you can cut a full circle into 60 equal parts, 60 degrees. The next thing is, if you've got 2 triangles and they share 2 angles, then they're similar, which means that one can be scaled up to the other, okay? And then if 2 triangles actually share two angles, plus the side in between the 2 angles, then they're actually congruent, which means you can take one and put it onto the other one, so they're really the same triangle. So let's start the proof. So the first thing we have to realize is that, well, this angle plus that angle plus that angle add up to 180 degrees. So if we add up the little angles here, the thirds, like up there, we've got the thirds kind of all the way together, they add up to 180 divided by 3, which is 60 degrees, right? So 60 degrees. Okay, just keep that in mind. Whenever you see red, green, and blue together, you see a 60-degree angle, okay? All right, now Conway's idea is to kind of go backwards with his proof. So he says, so we've got this configuration here. Let's just assume this works out. It's really a 60-degree, an equilateral triangle right in the middle. What are the angles that we see here? So for example, what's that angle here, okay? Well, we see a blue, we see a red. If we add a green, we've got 60 degrees. And then we need another 2 60s to make 180. So there's really no choice. It's got to be that, right? And the same sort of thing happens here for this and that. So here we've got these sorts of angles happen. There's no choice here, right? It's got to be like this. Now there's more angles here, 6 more angles. And we've got a couple of clues as to what these angles might be. So we can go around this triangle there and say, well, A plus B plus red should be 180, right? And we can go around this point here and add up things there. And so what do we get? C plus B plus 3 times 60 plus green is 360. 360, that's right. And there we've got another one, another equation, and another equation, another equation, and another equation. So we've got 6 unknowns here and 6 equations. And usually when you've got something like this, you can actually solve, except for this one you can't. It's almost determined, but not quite. So I mean, if you can actually choose one of those angles any way you want, and you can satisfy those 6 equations. That's not quite good enough. But what we can do, of course, we can have a really, really close look at some specific examples of these, and then maybe come up with a conjecture as to what these angles might be. And the conjecture is actually that they are as nice as possible. So our conjecture is that they're as nice as possible, like that. Okay? So this is actually going to be part of what we want to prove. So what we want to prove is that the trisections give this equilateral triangle in the middle, but in addition to this, we also want to prove that the angles are as nice as this. So why are they really nice? Well, just have a look at this. So this triangle here, for example, we've got red, green, blue, that's 60 degrees, plus 2 60s, that's going to be 180, right? If you go around this corner here, you've got 1, 2, 3, 4, 5 60s, plus another 60, blue, green, red. And it kind of goes all the way around. So the angles kind of add up all the way it's supposed to be, but in just the best possible way, right? In the best possible way. So we want to show that everything's best possible, right? So the triangle that is formed in the middle is equilateral, plus this nice distribution of angles all the way around. And well, it's suggested by this kind of setup what we're trying to try and do. We're actually going to try and go backwards, right? So we're going to start with just this triangle here in the middle. And now we're going to build up the rest and see whether we can actually get things fit together like this properly, okay? So first thing we do is we know, well, what the angles here are supposed to be. So we're going to just start with this, and that gives us this triangle here. And same thing around here, and same thing there. So we're going to just start like this, okay? Kind of try to reconstruct that triangle that we just saw, reconstruct it, and prove at the same time that it actually fits together like this, okay? Okay, then we draw a line here. And now what we really have to show is that this angle is red, and that this angle is blue. And once we've shown that, it looks already pretty good, right? Then we just have to do this 3 times. So we have to show that this angle is blue and this, and then one more time, right? Green and red. And actually the argument is exactly the same for this part and that part as it is for the first part. So once we've finished, this, showing that this is necessarily red and this is necessarily blue with our specific choice of angles, we're done, really. Okay, so here it goes. And now we go on fast forward. Heavy duty math, okay? But it's really just very pretty. Okay, so we take this triangle here, make a copy. Okay, so make a copy, flip it, attach it. Now we take that point here and pull it out until that angle turns into a blue angle. So like that. Okay, now we've got this big triangle here, and we just ask, what's that angle there? Well, it's again blue, red. If it added green and 260s, then it's going to be okay. So this is forced, right? This angle is forced to be what we expect it to be, okay? Just like before. Okay, now what about that angle here? Well, if you already look at what's here, it's pretty much what we want it to be. So it's also clear that this one has to be red and 60 degrees. So that's all fine, okay? Okay, so what have we got now? Well, we've got 2 angles that are the same, plus these 2 sides are the same. So this triangle here fits in nicely into this corner, but the only thing that we have to convince ourselves now is that actually these 2 sides are also the same. Then we're okay, right?
Because they could be different lengths.
They could be different lengths. They could be different lengths. That's the only thing that can go wrong here. So we have to really figure out that they're the same lengths, okay? So okay, so let's go back to this flip and attach triangle there. Make a copy of the heavily drawn segment, insert it in a second way. And now what we've got here is a isosceles triangle, right? That means these 2 sides are the same. What it also means that this angle and that angle are the same, right? So this angle is also this guy here, okay? Now we highlight something else. We highlight this triangle there. And so we've got an angle there, and now we can figure out what that one is. And it's clear that it has to be that one, pretty obvious, right? And so what that means now is that if we compare this triangle to that triangle, we get one angle in common, a second angle in common, plus the side in the middle in common, and that means that the 2 triangles are congruent, right? So congruent. And that also means that this side is the same as that side. Ta-da! And that means that this guy here fits in just like that.
Beautiful.
Beautiful, right? And that's basically, you've won here at this point in time, because now you just repeat, right? You take a copy of this, flip, attach, extend, run the same argument again. That means that this guy fits in, right? Run the same thing again, and you're done, right? So you've reconstructed this whole thing, and it all fits together, and so everything works. So probably the best proof of Morley's miracle in existence.
By John Conway.
By John Conway, yeah. By John Conway.
So
and animated by the Mathologer.
I'm starting to crave pizza with all these triangles, so we should go get some pizza.
Oh yes, salmon pizza. Okay, and this is Morley's miracle confirmed.